Okay, hello everybody. Welcome to the class today. So today we are going to be talking about sections 1 and 2, and then part of 3, hopefully, if we get there. And so, yes, of the book. Hopefully you all have the book. And so to kind of go along with the with what I'm going to be talking about of each of the sections, I took some notes down in here that I'll go over. There are also notes available. Oh, that's weird. Do you guys see that double line there? I don't know. That's interesting. But okay, yeah. So I have my own notes that I took when I was reading this yesterday, and then I also have the publisher's notes that we can also use to kind of discuss. And how that's going to look is like that. And we got figures, so basically all the pictures in the book, I have access to a bigger picture of, which could be nice, so we can talk about the figures. And in addition to that, there are some notes that the publisher basically has, the people that write the book. And so we'll use those. Why not? They can guide the discussion. So there is the book, copyrights. So I just want to make sure you guys are clear. I did not write these PowerPoint slides. They were available to me on the publisher's website. So yes, both of them. What I wrote is what I have on the iPad. So because of that, while I can share the iPad content, I don't know if I can share like a slide, like a PowerPoint file of the slides themselves. That I'll double check and see if I can actually upload them without getting in legal trouble or whatever. Okay. I did notice that the slides have the entire book, I think, on the bottom. So that's why I'm not sure. Like if I show you the slides here again, and I click on like this slide, down here is like a piece of the book. And it's literally like the next slide picks up where the last one is. Like the entire book is in the slides. So that's why I'm not sure if I can share them. It's not like it's just a random slide. The picture one, I'm pretty sure it's just pictures that I can share. But that one, because of that, it's like you can technically read the book off the slides. So, yeah. In fact, I thought it was supposed to be like some sort of speech that I was just supposed to say for each slide. But no, it's like literally the entire book. So, yeah. Okay. So, let's go ahead and open the first section. So, go ahead and open it here. Are we ready to go? I did not read the preface. I suppose that could have been useful, but I don't think so. Okay, so the first section is relatively short. It is talking about the differences between computer organization and computer architecture. And so, what do you guys think is different in your own words? So go ahead and tell me. And I will write down people's participation so that I can add the points in Notepad. Or better yet, how about this? You guys, when you participate, you can write a chat message down so that you say like who was speaking. That way you don't have to say your name out loud in the video since it's recorded and you might not want that. So if that's the case, just put it on chat. And then at the end of the lecture, I'll just copy and paste from the chat. Obviously, I'll see if people are putting things when they're not talking. All right? So go ahead. I heard someone was about to speak, so go for it. Well, so you know, it's a dangerous thing to say that organization is how things are organized, because we're kind of doing a circular definition, you know, because organization, organized is coming from the same sort of root word. So that's not quite. I could totally agree with what you're trying to say, though, as in like architecture is hardware and organization. So you are right in the sense, but I think that we can push the definition to something clearer. We have some people in chat saying computer architecture is a computer, hardware, and organization, everything interacts together. Yes, that's closer. And I think those are valid definitions. Not what the book says per se, but I think those are pretty valid. One of them, we have architecture is how it's designed and how we use the system. Interesting. That's an interesting one. Okay. Well, it turns out that the book says that you can think of the architecture as, from a more technical standpoint, think to like 218 as it being the instruction set. And it doesn't talk about how those instructions get accomplished. It just says that it has those instructions. So if there's an instruction to multiply, then the architecture basically says there has to be an instruction to multiply. And we're abstracting all hardware from this. This is like a software side of things. I mean, yes, you have to sort of get those implemented somehow, but you don't even have to think about that hardware. You're just saying, if I have an architecture for a computer, I am saying that these set of instructions will be included. Now, what kind of instructions can there be? Of course, if you think back to your CS135, we talked about there being 3 different types of languages. There's like the high-level languages like C++, Python, Java, JavaScript, whatever. And then you have sort of the assembly level languages, which are x86 and MIPS and those that you learn in 218. And then you have the machine code, essentially. Did I say medium? I meant low. I don't know if I said medium. So high, low, and machine code. And low is the assembly. And so the only difference really between machine code and assembly is that machine code is all binary stuff. And so it's just zeros and ones, and that's not very easy to read or work with. So with assembly, you have the advantage of sort of having these mnemonic codes, as they call them, which is just something that is easy to remember to do all these operations like, and again, this is where my assembly area is weak, but I think MUL is multiply in assembly. Correct me if I'm wrong. What other one is there? There's jump, which I think is JMP, which is your branching sequence in assembly. You know, please tell me if I'm wrong. In fact, there we go. Yes. Okay. Good. Oh, that's right. It is the unconditional. So what's the conditional one? What is that called? I forgot. Ah, okay. So jump is basically your go-to state, essentially. Yeah. Okay, there you go. Yeah, I can somewhat vaguely remember that. Yeah. So essentially, those are all your instructions. Those are the ones that when you wrote your language, you're like, I decided these to be my instructions. In fact, in the book, a little bit later on, I think in 1.2, there's a picture where they have a couple of instructions. I can go ahead and kind of show that really fast. Oh, it's a chart, so it's not on this illustration. Maybe it's on this one. Nope, there's none because it's a chart. But if you go on page, let me tell you, if you have the book already, you can look at it. It's page 16. I'll just kind of show it at the camera, but it's gonna be super blurry and unreadable. But at least you know what I'm sort of referring to. And the read screen is not helping. There's a chart, and that chart shows you a couple of potential instructions that you could have. And in this case, I don't know, that's x86 or what that actually is. I mean, that is IAS, so whatever IAS was running, which is, I think, 370. And you can see that you have the operation code, which we'll get to talking about that. And then we have the mnemonic code, sort of, which says symbolic representation, and then the descriptions, right? So when we're talking about architecture and organization, the architecture is going to be the list of those instructions. Now, that is more of like hopes and dreams. Like, yeah, we're like, yeah, we wish our computer had this and that and this and that. But organization is going to be really the one that actually kind of defines how we accomplish these things. So actually, I just thought about this. It's a lot like an architect and an engineer building a house. The architect does all of the designing side of things, like, you know, this is how my house is going to look. This is how, you know, how the room distribution is going to be. And then the engineer is the one that basically says, yeah, okay, I can accomplish this and this and this in this format, but like you can't just have this floating room in the middle there because we need to put a column beneath it so that it doesn't collapse, right? So like if somebody's building a house and, you know, that's your house, but then there's a second floor and then there's a room like that, but there's nothing in beneath. The engineer is like, yeah, no, we need to put a column here so that the thing passes code and doesn't collapse either. And so that engineer is going to be like, okay, we're going to get these rooms up here by doing whatever you need to actually make this actually stay there. So maybe we need some columns, maybe this has to be made of a certain material, and so on. So that is a lot, actually, now that I think about it, like architecture and organization, because organization shows you how you will achieve things. So the example that they give on the book, and then I did my own example, is multiplication. They say that you can think of architecture versus organization in the sense of a multiplication instruction. So architecture says we're going to have a multiplication instruction. It's going to be called mul or whatever. Organization tells you how you're going to implement that. So one of the ways that you can implement it is using your addition function, and then you can just kind of repeat that, not function but instruction, or some sort of device that can actually accomplish the addition. The other way that you can achieve you can achieve the multiplication instruction is you could create a special unit just dedicated to that. So you go into your chip level at that point, and you actually create a special area of your chip that just handles multiplication. And that was basically when they talk about transistors, you can think of that as all the transistors in a special configuration that achieve multiplication, right? That's one way to do it. The other way is just to use the addition section and then just kind of do that repeatedly, because that's another way to do it. Now, the multiplication one's going to be faster probably than the addition one. So you have to think about this. How many times am I going to have to multiply in this architecture? Is it going to be an instruction that is not really used a lot? And if that's the case, can I get away with doing repeat addition so I can save space in the chip? Or should I actually dedicate a piece of the chip to the multiplication instructions? Is that popular? And so that's what sort of the organization side of things is going to decide. And so you could have multiple computers with the same architecture, but running different organizations. Whereas you can't really have same organizations with different architectures, because that doesn't make much sense if that sort of makes sense of its own. And that's kind of what the first section is really just talking about. And I can show you in the PowerPoint here what they have. So we have computer architecture, computer organization, on the top left and the bottom right. And so we're talking about the attributes of a system visible to the programmer. So by attributes, you can think of that as the instructions. And again, you got to think about assembly and those kind of instructions, not necessarily high level language, because there is no, well, if it's kind of special, but there is no integer declaration at the level of, well, the kind of is, that's kind of tricky, but what will be a good one? There's no structs, at the level of assembly, and so that has to be converted into assembly code. So that's why this really only applies to the assembly level of things. Let's see what we got on the chat. So organization is like the building blocks, and the architecture is like the blueprint. Yeah, you could say that, as long as you understand that when you think of it in building blocks, you actually have to explain what those blocks are made of and those kind of things. And the blueprint doesn't necessarily have to explain anything on how it's going to be achieved, like what material we're going to use and things like that. It's just going to say there's a room here, there's a room there, there's a door here, there's a bathroom there, those kind of things. Could you compare this idea to encapsulation and the car example? Oh, I'm so, I wonder if that's because you saw that I had a car example down here. Oh, you can't even see it. But I did have actually an example of a car, but actually for talking about the hierarchy of things. So I guess that example will come up. I guess I wasn't that original when I thought about the car example. Sad. Let me go back up here. And then I have another example that I came up with for architecture. But before that, let's see what else is in this slide. So we have a direct impact on the logical execution of a program. The reason why that is architecture is because, again, your instructions, if you have a multiplication instruction, then you use it. If you have a multiplication instruction that is implemented using a special multiply section or just addition, You don't know that. You just call the multiplication instruction. But suppose you didn't have one. Then you have to use another method for that. Then you have to use the addition instruction. On your own, you have to figure out that functionality. So that's kind of what they're talking about by saying direct impact on the logical execution. As for the organization side, when they say the operational units and their interconnections, don't worry too much about what that means until we actually talk more about that, I guess, in 1.2. Yeah, I think that's good for that. So let me switch over to the iPad. Need to reorganize these things so that's easier to switch over. So my second example that I thought about was, how would this apply to sorting? So I asked you guys, how would you apply this sort of architecture versus organization to a sorting instruction and how you accomplish it? So go ahead. And here I can put this side by side so you can kind of see. So with a multiplication, the architecture is the multiplication instruction, and the organization is like a special multiply unit or calling other pieces of the hardware like an addition repeatedly. So architecture would be like the pseudocode you're reading and the algorithm you make, and organization would be the actual code. Not quite. You're thinking a little bit too hard with the architecture side. The architecture side would just be, well, actually, I don't want to say it yet. I want to see if anybody else wants to try. All right, I'll tell you, I suppose. It would just be a sort instruction. That's all it is. Sorting would, if you had a sorting instruction, it would just be called sort. And it would probably take the first word or the word or whatever that is in assembly of the list of items to sort. That would probably be something of what it would take if I was to guess. You know, that's all you would need, the sorting instruction. That would be your architecture. Now, as for the organization, that has a lot of answers on how you achieve that. That could be just a mixture of calling in like if there's some sort of swapping feature, like I guess your load and store in assembly, you know, that could be made up of a bunch of loads and stores, and that would be swapping. And then some sort of your as we were just talking about your jump, which I think is JMP actually, and then you know, as you were saying, if it's greater than, I don't remember how to write that, so if greater, I think it would be JMP if G or something. I don't know what the instruction would be for greater than. You guys post on chat. But yeah, so you could make it out of that, or you could have a little specialized piece of the hardware, such as there's a special multiplier. There could be a specialized piece of hardware that has a set of transistors that can do the sorting automatically for you, and then return you everything in a sorted manner. It could have its own little memory cell even and whatnot, so it could sort things out. And then you could run bubble sort on that, or you could run quick sort. But the point is that will be decided in organization. And so you could have a computer that costs $5 that does sorting using a bubble sort special unit. And you could have one that costs $50 that has a merge sort and insertion sort unit in there. And you know, that's more expensive because it's more transistors used, I guess, and that kind of thing. But you know, if you were to write a piece of code and then create the assembly code, I'm saying, or compile it into assembly, then it would work on both of those computers because they share the same architecture, even though their organization is different. That doesn't matter. All you really see as a programmer is this side of the coin. You don't need to worry about this side. This side is the one that all the engineers, like EE people and CPE people, have to actually make a reality. But we don't care about that. We don't care about them, right? So let's see. So the architect with the instruction, organization, instruction works. Yes, that's a good. That I like. Yes. So indeed, an architecture would be the instruction, and organization would be how the instruction works. Yes, like how it's made, basically. Good. I like that one. Well done. And cool. So that's basically 1.1, and that pretty much the entire one page is dedicated to that definition, essentially. I don't think there is a little bit at the end about microcomputers, but let's not talk about those yet. It says to talk about it in chapter 15. So if you get there, we'll talk about that. The other thing I want to point out, this is a good point, is and it's actually, oh yeah, it is a slide here on the PowerPoint. So switch over to that. The IBM 370 architecture, which still apparently lives today as the IBM Mainframe. Oh yes, that's in the bottom last bullet point there. So maybe you've heard of this, and if you haven't, that's okay. Now you have. And on the book, it says this architecture was first introduced. Well, it's something it says here in 1970. So that's when they first sat down and said, which instructions do we want to have? And they said, we want these instructions. And then they gave it to the engineers and said, make this a reality. And they're like, oh my God, that's a lot of stuff. That's a lot of transistors in there that we got to put. So that's going to cost a lot of money. And they said, oh, well, no, we want to be able to sell it to different groups of people, from like universities who may have a lot of money to throw away versus like your companies who may not really want to spend too much money, and so on. And so they introduced a number of models. And so from like, you can think of like, cheaper to more expensive. And they were running in the same architecture, which meant that some of this, you had the ability to do anything in all of them, but because some of the organizations were different, then they were potentially, let's say they had a sort function. They had the small transistors, the one that uses the slowest amount of transistors for their sort instruction per se. And I don't think that any assembly languages really have sort in them, but they might. Who knows? Maybe like if it was encryption based, it could be useful, but not really. But yeah, if they had a sort of a sort instruction there or a multiply instruction, they did it in the simplest sense, with the least amount of transistors. So they reused a lot of things, which makes it slower. Other ones had specialized sections for just about everything, but because there were more transistors, it was more expensive. But the cool thing is that when you wrote a program for 370, that architecture, then it would work in any of these computers. And in fact, some of them would do it faster than others, but it would work for all of them, with the exception that we know that memory is also a thing, right? So, I'm assuming that the more expensive models have more memory. And so that's another thing, but that's besides the point, because you can buy that later on too. And that was actually a thing. It says could upgrade to more expensive models without having to abandon software. And that was very important because think about it from the point of view that this was a new technology. And so you create this machine that runs on electricity, and so you're creating these programs for it, right? And you spend a lot of money because this is new technology to create these programs. And because the technology at that point was like all over the place, explorations wise, if I'm gonna spend maybe $100,000, on paying these developers to create this little program that is useful for like doing your taxes or whatever, and then I sell this program, right? I'm not gonna make my money back until like people buy this for the next maybe 5 or 10 years. So if the architecture gets changed every year, then my program's no longer gonna work, and all my basically work doing this is useless unless there's an easy way to convert it to another architecture, which there might not be, because they might just completely switch over everything and just throw something totally unrelated to this as a new type of computer. And that's a problem that we still have today, actually. Somebody, I don't know, was it the 202 class or the 219 class that they were interested in augmented reality? And VR and AR are going through a lot of changes in the sense of how they're working. And so that's why some people are scared about investing in these things, because this is going a little bit beyond just architecture, but devices are changing in terms of what they can handle, and if you and sort of what they need to function. So if you code something for specific hardware, and like the Oculus Rift, for example, and then the Oculus Quest comes out, how easy is it to port it over, because people won't be using your device in the future. And so these were the same concerns that people had in the 70s as well. And so IBM was like, don't worry, guys. We are going to keep this architecture for a long time. So you guys come to us, code for our architecture, and we promise you that even though we will modernize the computer so that we can keep up with whatever technology is being developed in these years, your programs will still work. And not just that, they'll work even faster when we release the newer technology. And so that brought sort of confidence, and it really popularized the 370 architecture because of that. Because I could say, okay, if I'm going to spend money investing for this architecture, then I will be okay in the long term. And to the point that even today, the architecture has survived. So some of the programs that were running back then could still run today. And that's what's known as the IBM Mainframe. And IBM is a company that has gone through their own set of adventures. And maybe we could spend some time talking about it, or something on Friday with Sam. But yeah, they're one of those companies that has gone through definitely some interesting high and low points. And so that was basically the big thing about the 370 that was up to today is very popular. I don't know if you guys have any questions. And we got somebody says, like Apple's new ARM processor in their MacBooks. You know, Apple is weird. There is definitely if you go to 1.5, they start talking about the ARM architecture, which that was actually a big change. But ARM isn't necessarily limited to just Apple. You know, ARM is skipping a little bit ahead. ARM is a completely different set of. I mean, you took 218. You guys took MIPS, right? MIPS versus x86, and you can see how very different those architectures were, right? I do believe ARM is pretty much on the MIPS side of things, and so that was a big change where like people had to just about to code everything again from like everything. There was no programs for that, so we just had to go over and start everything again. And so, you know, I'm assuming that Apple maintains the same architecture these days, because otherwise, if they release something, then zero programs would work for the architecture. Okay, so like that means that Photoshop, Notes, or whatever the Keynote and all those things, they would have to remake them from scratch almost per se, or at least find some way to translate instructions. So nowadays, what really ends up happening is, yes, architectures get updated, but the updates are so minimal that they're kind of backwards compatible. So like when you hear about Intel, because that's more, I know more about Intel than Macs. I don't like Macs, but I have a Mac, but I don't like it. Intel, you know, releases different architectures with a number in front of it. So when you see like i5, i7, that's just variations of the same architecture. But that's more variations of the organization, actually, than the architecture. Although there are some instruction differences, I think. So it might be technically different architectures by the definition of the book. But ultimately, when you see like the number afterwards, so the i7, like for example, I have an i7-6600K, right? But that's old now, I think. Now they're like there's even an i9 that's like 99 something, and or 9600K. That might be the equivalent. And so each of those numbers, you know, they even have nicknames like Skylake and Haxwell and all of those. Those are different architectures, but I would say that 90% of the instructions are the same. And if anything, they might add some extra instructions for special cases. Like I think they've been adding some security instructions for like built-in chip encryption and decryption, that kind of thing. Because a lot of people are very security sensitive, I could call it. You know, they care about security more. But while that architecture is different technically, that doesn't mean that everybody's got to code everything from scratch again. Most of the things will work, and they really only have to recompile, and the compilers is kind of what you have to update to add those extra instructions and take advantage of it. So it's not that big of a difference now as it was back then, where things could completely change. Nothing better than starting from scratch. I agree, but it's also very expensive. So anyways, that's pretty much 1.1. So now we get to 1.2, which was structure and function. And let's see what I have about that here. Okay, so I have my car example, and I'll get to that. But first, let's just look at the basic definitions that we have in the book. So structure and function, and this is one way to look at things. I don't want you to think that this is like the only way to look at some of these terms, but you know, they have to kind of, you have to start with some even ground, right? Like you have to define some things to kind of build into more things. So you have to pick one way or the other. And so this is the way that they kind of pick to do things. This is structure is the way in which components are interrelated. And function is the operation of each individual as part of the structure. Okay? And so you can see basically the same thing here on the PowerPoint here. And so what do you think that actually means? Like function and structure. Yes, and they did, by the way. I was just thinking that when I was talking about the security thing. Intel did have an issue with one of their instructions. I think there was at the lowest level of the chip, which is something that you can't change with an update. They found a security flaw, which I think just defeats all encryption purposes. But it's not that easy to get into. You actually need physical manipulation of the chip to get to it, as far as what I read. So it's not like somebody can just hack into it. They actually have to go into the chip and finesse with it, and then they'll exploit it. But that also means that everything that you encrypt is not secure anymore. So that's a big deal, actually. I think everybody just paid money to hide it from the news. But yeah. Oh, I'm glad that you brought in the von Neumann, because von Neumann is going to come up. And that is more of structure. Oh, well, that's what you said. So yeah, we can actually jump to that. So this is von Neumann's diagram, at least the top circle. Okay. So yes, structure is going to sort of be how things are connected. Okay. So if you remember von Neumann's diagram, and I can draw you a more of a version where you might have seen before. You know, so let me zoom in here so we have more space. So von Neumann's diagram is how the main components of a computer work together. Okay, and so von Neumann says that you have your CPU, and nowadays this is sort of I wouldn't say it's wrong. It's just become part of the language. We think of CPU as the entire box, like the box that our computer runs on. But while yes, that isn't the normal jargon per se, lexicon of today, we are thinking of CPU as just the actual chip itself, and the motherboard is something completely different. And then we have in there the RAM sticks, right, which we call memory. I zoomed in, so now the text is, the ink looks very thick. But yeah, so von Neumann's diagram says that we have a CPU, we have a memory, and then we have I/O devices, which can be a monitor, that could be an output device, and then input device could be a keyboard and a mouse. Technically, I suppose an actual printer would be an output device as well. And then it doesn't make any mention about internet, but nowadays that's something that we have to think about. And it actually, I'm glad the book mentions it. I think they call it comms. Well, actually, I wrote it here. Communication. Von Neumann's diagrams. I don't know. I thought I wrote it somewhere, but basically, oh, here we go. Communication. So data movement, because data movement is a better way to represent input output and also communication, right? Because you could say, if you want to be a purist of the von Neumann diagram, you could consider input and output to be all, not just locally. Like you could say, if you're, let's say I am because I have a VPN set up and I have my printer connected to that. So in theory, I could be anywhere in the world and print something out. And I actually set that up because sometimes I need to print things out not where I'm at. And so technically that's I/O. I mean, like I am sending some output somewhere in the world, right? But obviously it's kind of different than if I was sending something just, locally here, right? Or is it though? I mean, is it? So it's kind of debatable. So let's see. Structure is how everything is connected, like a jungle gym. Function is how it works, monkey bars. Yeah, I would say like a gym in general. Just like a gym. So the gym is going to be, you got your gym and you got the different parts, and the function is what each thing is like gonna do for your body. Like, if you're trying to work like your legs on leg day, you got the Stairmaster or whatever, then that's the function of that individual part, and it's connected in the gym. And the gym, you could say, is your exercise mechanism or something. Okay, so the example that I came up with for that, which is not original, I suppose, that sad face, was the car, right? So your car has kind of main different parts. And usually, and this is kind of what they talk about in the slide in the book, is that it usually has some sort of hierarchy to it, because it makes it easier to explain something when you're talking about it in a hierarchy point of view. So whereas the von Neumann diagram just says that there's memory, there's a CPU, there's an IO device, we're going to look at it more of like, okay, cool, there's memory. But now within that memory, how is that handled? Within the CPU, how is that handled? Within the IO, how is that handled? And there's two ways we can look at it, from the top side down and from the bottom side up. And most people agree that it's a lot easier to look at things from top down system. So basically, divide and conquer, you break a big problem into smaller problems, you're working from the top to the bottom. You know, although technically when you're solving those problems, you work from the bottom up, right? So like if you need to code merge sort, or not merge sort, maybe quick sort. If you need to code quick sort, you need to find a way to pick a pivot, and then you need to find a way to do your partitioning, which there's two there's Lomuto, and then there's Hor's method, and then you need to find a way to keep this information, like if you're keeping it in an array or a vector and so on, right? So when you're solving the problem, you're like, okay, I need a sort function, and then I need to figure out how to do these specific parts. So that's how you represent it. But when you're actually solving it and implementing it, you actually implement the pieces together, test them individually, and then put it together and test sorting as an entire thing, right? So it's easier to plan things from top down, but it's easier to implement them from bottom up, okay? And so the example is if you're trying to design a car. So in a car, you're like, okay, what do I need in my car? Well, I need some sort of motion to be able to move, and I need some kind of engine, right? And that doesn't have to just be the engine, but just basically the technology to be able to move the car. It could be like the Flintstones, and it could just be a hole in the ground so I could move it with my feet. I also need to be able to control the car. So that was going to be sort of your input-output, right? And then I need payload, because either the car can, it could be a truck where it has actual payload to carry plus the driver, but it can also be like just a driver car where it's just carrying a passenger, and it might have space for additional passenger, a pilot per se, and additional passengers, or a trunk to actually take some cargo, right? Or it could be just a race car, like I guess what I drew, where the only payload is just a human that you need to consider the race. That's interesting. Is there any races? Like, they should make a Formula 1 where there's no driver. That would be 100% safe in theory, right? And then it could be just like remote control, but they still have a real car. Because that'd be cool then if they crash. It's like massive explosions or something. So I support that, I suppose. It'd be safer too. Like I said, no real passengers. Yeah. But okay. So anyways, so you think of it like that much, right? You think about like, I really don't like how the thing on the bottom is like that. I don't know how that. Maybe it's because I wonder if doing this will fix that. Let me try something. Yeah, that fixed it. So it's because it was off the screen and it left that little line there of pink. Okay, so yeah. So now that you kind of designed that, you're like, okay, cool. You tell that to your engineer. You're like, okay, we're gonna have this car, blah blah blah. Okay, but then the engineer has to figure out how is the actual engine gonna work. Is it internal combustion? How am I gonna cool the engine, and so on. And even there, you can go into more of a closer view. So let's say we're talking about the engine block. The engine block is going to be made up of other things, like you have the pistons themselves and other things that engines might have, which I don't know because I'm a CS person, not a car person. But the point is that you start going into the hard details of how this thing actually needs to work. On the I/O side, that's a little bit easier, at least for me to understand. You have the steering, which can control your your y-axis per se, if you think about it like this way. And then you have your x-axis this way. That's going to be your acceleration and braking, and potentially a gear to switch to the reverse. And then from there, you still got to define how those work internally. Is your steering hydraulic or pneumatic or is it mechanical, or how it works? How your acceleration actually communicates with your engine, right? So how do you actually communicate? That's a good one. How do you get acceleration to communicate with the engine? Well, for that, you're going to need some sort of line, right? And in the terms of the book, and for a computer, they call this the bus. I think it's just main bus or just bus. System bus, yes. So it's on top of page 6. Interconnection is by means of a system bus, consisting of a number of conducting wires to which all the other components are attached. So that's going to be your system bus, how you communicate between this. And it's very important to communicate. Now, with a real, if we're not doing our futuristic no driver car, technically, in theory, you also have a wire running from the payload to the control, potentially. Not to the engine, but at least to the control, right? Because that's going to be your driver actually pushing the accelerator, right? Which technically, yes, the accelerator itself has a way to do it, but you could also say that the payload in this special case is the one. But we'll get rid of that just because it would actually be a little bit more confusing than helpful. So we'll just say that the acceleration is kind of getting the input there, okay? And then the payload again is going to be, if we said like passengers and so on. Now we don't need to define unless we're trying to like define what a human is like or something. I think you can improve the example by adding fuel as part of the storage. Yeah, that's a good one. I agree. Let's throw in fuel in here as well, because you need fuel for the engine to work. Otherwise, you got nothing, right? So yes, fuel is a very good, I would say, the wet payload versus the dry payload, because that one is actually going to vary, right? If you think of a rocket, wet payload, they talk about fuel because that's going to be changing in the weight as it burns, versus dry payload, which is what are you actually carrying to space or in that stage and so on. So yes, I think that's a good one too. Yeah. And so, yeah, okay. So how are we doing? Are we good on this? I mean, this is very, very, very basic stuff. But still, I think it's important that we spend a little bit of time to make sure that we understand before we jump into the crazy hardcore stuff that we're like 5 pages from basically here. So switching back to the PowerPoint, and I don't make it full screen because that would be an extra effort to move around. We see something kind of important here. Designer only needs to deal with a particular level of a system at a time. And that's the same thing that when we're solving a problem, like I said, with quicksort. You only need to worry about having your partition function work. You only need to worry about having your pivot choosing to work, right? It's a lot easier to figure out to design problems and then put it together, right? And so, yeah, that's pretty much what that says. So, let's talk a little bit about the functions of a computer specifically, okay? So there's 4 main functions of a computer, and I also had them here in my Twitch thing, but I didn't have any more details about them. Those actually I think is better in the PowerPoint. So we have data processing, and I could have asked you what these were, but I mean they're listed on the book on bold, so you would have just seen that. So the 4 main functions that we need are process. The 3 of them are data related. So we got data processing, data storage, and data movement. Okay, so what does that actually mean in practice? Storage is the easiest one. That's, as even you said in your example, is you need to store the data in the computer somewhere. Now why? Well, even if you're just processing data, if you say, oh my computer doesn't need to store anything, it just processes data and immediately gives you back to you. Like let's say I feed it in some tape and the magnetic tape, and then the tape comes back out with some holes on it or something, and it's not really storing anything. Not quite true, because even if it's just processing, it needs some form of storage temporarily while it does the processing. Otherwise, it can't even read the data. It's like the act of you reading the data is you actually storing some data temporarily. That applies to humans too. Say you don't care about anything, you're not trying to memorize anything, but somebody asks you what 2 + 2 is. You need to store in your head for just a second that the numbers you're adding are 2 and 2. And that way you can then compute 4. You know the answer before you even say it for a tiny little second. And then you say it. So you're storing both the input stuff and the output stuff before it comes out. Now, whether or not you're going to remember that tomorrow is a different story. So that's the main difference between what we have as a short-term and long-term storage. Short-term is usually when you're just processing the data, and it can be some in-between stages of the processing. Long-term is when you're actually told, okay, store this information, memorize this. Or in the case of the computer, when you're storing something on the hard drive, or, well, I guess hard drive versus solid state, and so on. Memory, that is kind of in between, because you could think of it as a short-term, but if you're leaving the computer around permanently, you could also use it as a long-term, albeit a little bit dangerous, because when you lose power in memory, it loses the data. Although technically, what what some forensics do is you don't lose the data immediately. If say you raid somebody's house and they have like some illegal stuff in their computer, what you can do is you can freeze the computer, like literally just shoot liquid nitrogen at it, and it freezes the RAM, and it actually will within like 30 seconds or so of you shutting a computer down and the power slowly bleeding out, you can still recover some of the contents of the RAM that way. It slows the movement of electrons, and so you basically can still take information from it. That's pretty cool. So that's actually a real thing. So that's pretty cool. You can Google it. So yeah. But anyways, so yeah, it has to, definitely. Okay, so that's storage. Processing, of course, being kind of the useful side of a computer. I mean, storing information is a useful thing, don't get me wrong, but processing is, I think, more of the real power of a computer, because if I want to just store data, I can go buy a warehouse, a bunch of file cabinets, and store data. Got it. Don't need a computer for that. Processing, that's where you can really take advantage of a computer, because processing means the input that you're taking, you're doing something to it, and then you're getting something back out of it. That can be just about anything. You can store data, you can compute arithmetic, you can make data retrievable in a better way, tons of things you can do, okay? So processing is where the real power of computing comes in. Now, to achieve storage and processing, you need what's known as data movement. Basically, how do you move the data around from storage to processing and technically from input to output? So when I feed it the data, I need a way to actually communicate with the CPU the data, right? So that's going to be the input output, right? And so that is actually technically its own sort of difficulty. Like, how do I actually, if I could just like say, okay, I'm just going to speak to this box. I have a chip here. I'm just going to speak to it. And assume that it's going to understand me and compute things, and then maybe like speak back to me. But it's just a chip. It can't do that. You need a microphone like I have that you can speak to, and then if there was some sort of voice to text feature, then it could actually store it as data. Or if not, then they can just record the audio directly, right? So you need to have some sort of input for that, and then output being if it wanted to translate to a different language or something like that. Maybe that's what I wanted it to do, right? And so basically, that's going to be your data movement. That's going to be your input output. But also, as I was saying earlier, if you're communicating over a longer distance, such as like I said with my remote printer, or potentially sending an email out to somebody, or in the case, doing a lecture online, that is also I/O. My input is me talking to the microphone and the camera recording me. The output in this case is somewhere else in the city. Maybe some of you are not even in Vegas right now. And then you receive that image and you receive that audio, right? And there might be processing involved to compress the data so that it can be sent faster over the internets. So, yes. Is this chemistry class? Why would, I don't know. I don't know why I said that was chemistry related, but yeah. Oh, because of liquid nitrogen, yeah. Yes, you physically freeze the machine to save its state. I guess that's one way of doing, what do they call it? Sleep mode. So yes, that's your data. That's your four main. Oh, I actually didn't mention the last one. Okay, so this is all cool. You have all these great things in your computer. You have processing, storage, and movement. You need to find a way to actually control these things. And by that, I'm saying, how do you actually get them working together? Like, here's a microphone. I just throw a microphone together. It's like, if you guys have seen the potato picture of the computer potato picture, it's just basically a potato and somebody sticks in it a piece of RAM and some wires. Let's see if I can Google it. Potato machine. Actually, let's not do that, because what if something scary comes out? So let me do it on the side here. It actually gave me how to make French fries. Potato computer. Yeah, here we go. So that one. So somebody obviously probably like, check out my build, and then they post that picture, There might be variations of the picture. And so let's analyze this computer, shall we? We got a piece of stick coming out of it, which I believe is the RAM, random access memory. We got, what? That's weird. I'm assuming this is some sort of hard drive. No, it says remote access PC card. So I guess it's a Wi-Fi card? I don't know. I think that they're trying to make it seem like that was a hard drive, but I don't know. Then we got some I/O devices. We have a VGA cable that is usually used for a monitor. Then we have a mouse cable. This is old school mouse cable. So that's input device, whereas this is output device. This looks either like a USB or HDMI. So it could be just for about anything, input or output. And this seems like a speaker cable. So there's output as well. And then we have a cooling sink, I guess. And I don't know what that is. Yeah, who knows what that is? Yeah, no, this build looks really nice, actually. That's a very well shaped potato, too. So, yeah. So, it's not enough to just throw things together. Because, like, what is the problem with this build? The problem with this build is that it has no motherboard. And because it has no motherboard, you can't communicate the processor, which is the CPU, which is the potato, with the RAM, with the speakers, with the printer, or with the monitor, and so on, right? So you need a way to organize all of these devices and have them work together. We already said that the system bus is the communication. And by the way, the system bus in the computer is literally the RAM, the motherboard and the cables going inside of it. But we need a way to organize everything. And so that's going to be the fourth functionality of your computer that you have to have. And that's your control. And it's some sort of control unit, as it says here, that manages the resources. Resources being all your I/O devices, your RAM, your storage, and all of that. And orchestrate the performance, that's a very fancy way of saying it, of the functions. So basically, organize how things communicate and how they work together to actually achieve these tasks. So that's the hardest part, I frankly believe, of the computer, is the control side of things. So then that's the function side and the structure side. So as I said, you have your sort of von Neumann style, which is your I/O, main memory, and CPU. And then the thing that puts them all together, that control, is part of the CPU, but also the system bus that allows you to communicate in between. So then the book goes into more detail. So it's kind of like an enhanced thing. So enhance, and then it becomes bigger. And so we get this one. This is the CPU. And in this class, what the main goal is, we're going to be looking at each of these more carefully and how they work and what's good and bad about each of them. So we'll spend some time. I don't know much about the system bus, but we'll definitely spend time on CPU, on main memory, and maybe a little bit on I/O. I don't know. I have to look at the syllabus again. But basically, the chapters are divided into this method. So, just for now, let's go ahead and look at the CPU. What is the CPU made of? So the CPU is made of, I suppose, four parts. And now it's getting a little bit harder to read. So we have three components. And those three components, and this is on page 5 of your book, is you have what is known as the arithmetic logic unit, which does the math and the processing, actually, of the CPU. So I don't know if I said this before, but just about anything that your computer does can be boiled down to just three things: doing an and or, and a not. So I guess that's hard to say, so maybe I'll write it down. These three things. That's all you need to do just about anything that you have in a modern computer today. Those three things. And those three things are truth tables. And I hope you guys know this, but just in case, the and can only work if you have your left and your right is true, then and becomes true. Otherwise, it becomes false. The or on the other side is if one of the two sides is true. And then the not is just flip something, flip an individual thing into the opposite of coming in. So, if you have, I don't know, I don't remember. I think this might be or, and this might be and. I don't know, but whatever the symbols are in the CPE people world, then you can think of it like and that. And so if these are 1 and 1, this becomes a 1. If this is 0. And this becomes a 0, and so on. Although if this was an or, then this becomes a 1 in this case. And then for the not, if you have a 1 here, then it becomes a 0. But if you have a 0 here, then this becomes a 1, right? So entire computer, yeah, I get those flashbacks. Entire computer is built of this. Those three little thingies are built. What are these, by the way? These are transistors. And so when they say a computer has like 5 billion transistors, it means it has 5 billion of these little logic gates, as they're called. And that's you'll read about it when you read 1.4 tonight. But those are basically the heart of the computer. These are like your cells. You know, your human body, you have your cells, which I guess is the smallest unit per se. Although there's specialized cells, so it's not as good of an example. Maybe atoms. Yeah, sure, atoms. But in a computer, that's going to be the smallest piece of what of how this works, right? So everything can be basically done with using these two tables. And now, yes, if you get your flashbacks from CPE, you put these in a specific manner, and you can create a little multiplier or a addition or subtraction. Or, better yet, a flip-flop, right? What is a flip-flop? A flip-flop is a way that you can, what is known as a memory cell, which you can store data. Because here's the thing about electricity. You know, you can just constantly flow it, or you can turn it off. But most of the time, it's at a certain frequency, so it's flickering back and forth. You know, so you got like a light bulb is usually flickering at 60 hertz. If you're in America, if you're in Europe, it's 50 hertz. And so if it's something that's flickering on and off, how do you keep something on? Like, which is memory. You know, you can keep, say you want this to stay as 1, even if you change here to 0. Well, you can use a NOR gate, I believe, for that. This is where my CPE knowledge ends. But I think it's called a NOR gate. And then I believe there, if you do something like this, it becomes a 1. And then if you switch it to 0, it still stays as a 1. If you want to make it a 0, I think you got to switch this one to a 1. And then this becomes a 0. And I think the fail state is if you try to put 1 on both at the same time, which you can fix by making a more complicated flip-flop. But yeah, so you can do memory this way too. You have a question. Does each transistor relate to a specific gate, or can you use multiple gates in one transistor? No, each transistor is just one gate, and they're usually designed differently. So when they design a transistor, the tiniest thing, and maybe you can Google a picture of a transistor. Well, that's going to be macroscopic nowadays. But let's see what actually comes up when we Google transistors. Oh, well, here's one that they will use like a breadboard, I suppose. Yeah, why not? Obviously, this is not the one that you have in your CPU, because, I mean, that's pretty big. But, yeah, why not? This is, here, this one's good. So you got a transistor, and it's got 3 little prongs there, okay? And so you have sort of the input. You should have at least 2, I don't know, this is CPE stuff, but you have 2 inputs and you have 1 output, okay? And so if this was an AND gate and you feed it electricity on both of these wires, well, I guess there's 2 ways to define it. You could define it as no electricity as being a 1, and then if you close the circuit where there's electricity, it's a 0, but the vice versa could work as well, where you can consider a 0 when there is electricity and 1 when there is not. But either way, when you feed, if you're saying feed 2 1s, which is electricity, then this will have electricity flowing out of it. Whereas if you don't feed it electricity here, then this will have no electricity flowing out of there. And so essentially, this will be 1 transistor, and it's built to work for just an AND gate, or just an OR gate, or just a NOT. You can't just flip a transistor. Although there is what is known as a FPGA, field programmable FPGA. What is G and A? I don't know. But basically, FPGAs allow you to reconfigure those logic gates by being a sort of more of a simulation than an actual thing. But it's much faster than actually than coding in software level. I just remember that. If you took CV100, which I think you all have at this point, then they talk about that, or they will if you haven't taken it. Field programmable gate array. Yeah, gate array. Gate. And gate, again, is another word for transistor. Gate is more of the theoretical thing. And so gate is like, think of gate as like your architecture, and the organization side would be actually the transistor. Gate is like what we want. Transistor is how we achieve the gate. So an array being, because it's a bunch of them, and they're sort of in a little matrix thing, and then you connect them how you want, so that you can actually build the chip that you're doing. And FPGAs are very good for prototyping stuff too. And for, I guess, if you want to prototype like a Bitcoin miner or something. So somebody said something about a automata. So don't think about automata for now. That's going beyond into other lands, but not quite the way that you said pushed on automata. Okay, that's something very different. So anyways, back to the picture. Arithmetic logic unit is made up of transistors, and it is going to do the math. And because it can do the math, the arithmetic, then it can do just about anything in your computer. Because again, you can convert anything in the computer into basic math and basic logic. So that's what that is made of. However, we need to store the data before and after the arithmetic is done on it. So that's what we do on the registers. So the registers are going to be a little bit of memory cells. You can think of them as flip-flops, but it's more advanced than that. And we will talk about it when we get there. But you can think of that as where the data is being stored. And so you store it there into your register, then you feed it into the ALU to do the computations, and then you get the results back in the register. Assembly time. With assembly, you do your load D word, it loads into the ALU. The ALU has, of course, some internal thing. I think if we go a little bit further in here, I seem to recall it having a diagram. Yeah. When we get there, we'll get there in a minute. So it has somewhere to store the data. Okay, we'll get to how that works. But you can think of, even though it's iffy, you can think of it having like a little tiny internal register to keep stuff in there. Okay, although maybe it can do it directly there. But anyways, this is where you store the data. This is where you do the computations, and then you have a cable, which we call the internal bus versus the system bus, which communicates these two together. Because you still gotta find, again, these are individual parts that you gotta hook up together. This, of course, is microscopic at the CPU level. Okay, because think about a CPU this big has billions of transistors in there, and your control unit is going to be the heart of the computer that figures out what to do next. And again, we'll talk about that in a second once we get to that picture. In fact, here we can zoom in on the control unit and see what it's made of. So we can see that it's got 3 parts, and we have what's the sequencing logic. So that you can think of like, if you have a program, you have an instruction to run, and then you have another instruction to run, and you have another instruction to run, right? So that sequence of logic is how you do things. And so the control unit also has its own sort of sequence of things to run. It has its own registers and a decoder. The decoder is what converts the opcode, the assembly code, into actually what wires to turn on to use what parts of the system. And by that I'm saying like the multiplication unit. It has to enable that piece of the chip and so on. And then it has some sort of memory of its own as well to know what to do. This will get expanded in a second here. That's just talking about the von Neumann stuff. Basically the same thing that I just went over. But here we can, more official terminology. Control unit controls the operation of the CPU and hence the computer. I don't know, that doesn't sound very official. Performs the computer's data processing functions. What I said. Provides storage, CPU interconnection, some mechanism that provides communication. Yeah, that's not too technical. That's pretty much what I said. I guess from there, that's true. They do talk a little bit about what could be a multi-core computer. For that, let me. I think there's a picture in the book which I have under the figures. This one that can show you. So far we're talking about what will be a single processor chip. I think they call it single processor unit. Something like that. Basically, we just have one ALU. Or better yet, one CPU. Okay? But nowadays, that's not enough. Because when we talk about Moore's Law and all of those fancy things, the too long didn't read of that is that one of the ways that we were speeding up computers back in the day was we were just throwing more transistors in the same space. And it was halving every 2 years and so on. That worked great until the quantum realm hit us hard and slapped us in the face and said no, you can't do this anymore. Because we got so small that we're actually having problems with atoms and electrons, specifically getting outside of cables and just going through walls. Like you have an electron that's going through a little wire. Not anymore. Now it's just literally going through a wall. Like it just faces through. That has a term, which I don't remember exactly. Quantum phasing or something like that. And, you know, you can go... I do want to actually, if we have time, like the last day or something, talk about quantum computing. But... which is unrelated to the problem that I'm talking about. But I just remember that. But essentially, we got to the point where we got so small that we can't go smaller. And because of that, that's not one way that we can speed computers up. Because one way to speed it is just add more to it. You know, add more transistors, more power. That we kind of hit a wall, or at least we hit a big barrier that is slow to push versus like just running through. So the alternative to get more power is just to get more of things, right? So now, instead of having one CPU, we can have two CPUs. But that, of course, adds a lot of complexity to our system because now we got to organize two things. So it's kind of like saying, okay, you know, we need to move 1 ton of cargo. Well, that's not a lot, but let's just say it was a lot. We need to move 1 ton of cargo with this car. But the car can't handle more. So what do? We put a bigger engine, right? But it gets to the point where the engine is too big, so we can't make it bigger because it doesn't fit in the car. So what do? Well, we have 2 cars. We just get another car with the biggest engine, but we still get another car. And then we just kind of hook them together with some tie wraps and then put the cargo between both cars, and now we drive. Or we could just chop the cargo in half and put it in 2 cars. That's another way to solve the problem of more computing power. And that is currently our the best idea that we have outside of quantum computing and that fancy stuff. And so that will be known as a multi-core computer. And so this here is an example of that. So we got our motherboard, and it has our main memory, I/O chips. You can think of that as like hooked up to whatever, monitor, audio, your sound card per se, your graphics card for video, and so on. So that's what they mean by chips. And then you have your processing chip. Your processing chip, because it's multi-core, is going to have more than... You could think of it more than 1 CPU, but it's a better way to explain it as more than 1 core. So that's a much better term to use, core. Core in the book says is an individual processing unit on a processor chip. A core may be equivalent in functionality to a CPU on a single CPU device or system. Okay? And so, what does that entail? We haven't talked about cache, but we will in a second. But ultimately, that means that you're just going to put a bunch of cores together, but then you have this sort of shared cache. And then each of the cores is going to have its own arithmetic logic unit, which we talked about. And then it's going to have probably its own registers as well. And an internal bus, as you saw before. However, it also needs communication between the different cores. And so that's going to be an extra thing. And it doesn't necessarily, although it probably will have its own control unit as well. So... here's just a random example of a computer that looks nothing like what people have nowadays. But just so you can see, in case you've never seen a computer before, that'd be surprising. I guess, correction, if you've never seen the inside of a computer before. This is your entries for the RAM. These are your hard drive entries. These are for hooking up to USBs. This is for video. More than likely you have a HDMI. You have your Ethernet controller, and you probably have Ethernet ports here. Yeah. PCI Express is useful for I/O stuff or expansion slots, so you could have a graphics card there. You could also have, you can even put a hard drive in the PCI Express slot. I believe that that's a thing, actually. And then, of course, you have to have somewhere your CPU, but usually you don't see it because the CPU gets really hot, and you got to cool it down some way. And one of the ways that you can cool it is just by shooting air at it. But if you shoot air at the CPU, it's so small that it has a very small surface to cool. So what you do, you increase that surface. Because it's metal, and metal conducts heat very well. What you do is you hook up to a bigger piece of metal that has more surface, which you can then blow air to and cool it down quicker. And so most of the heat sinks, as they call them, have a lot of surface to them, which look like car radiators, because that's another reason why car radiators look like that, so that they can have more area that can be hit by air to cool. And so that's why heat sinks look like big compared to the CPU and so on. So yes. One thing I'm not sure is how multi-threading works. Well, we will talk about that when we get there, but within each core, you have what are known as threads. And when you say multi-threading, is you're running multiple threads. A lot of the times, I believe Intel CPUs at least have 2 threads per core. That means when we talk about pipeline, again, you will learn that before the class ends, that's for sure. But until we get to talk about it, the overview is that there's a thing known as pipelining, and you can think of these threads as running their own operations, and a core can sometimes do more than just 1 thread per se. So you can think of it that way as well. So anyways, don't worry, we will talk about it as well. Well, I know AMD has it, but I'm more familiar with the Intel because I guess they're cooler. I don't like AMD anymore. I used to like them, but then they betrayed me. My computer died. So let's talk about. Let me see what we have to do here. We need to talk about cache. There's some definitions. I'm surprised that the PowerPoint didn't talk about these definitions. Oh, well, there's core. Yeah, so core, individual processing unit. I guess the only thing when I was reading this that I was like, I need to clarify was I think it had to do with the word processor versus processing unit that I thought was a little bit confusing. Yeah, so in the book, they define processor as the actual physical piece of silicon, as it says there, with 1 or more cores. But each individual core, you could technically call them processors as well. If it was a single core CPU, which would be like a just no multi-cores and whatnot, you would call that the processor. But here, they use processor as the entire thing, and then they use the individual term as cores, okay, or processing unit. So yeah, I remember now. Yeah. So the confusing part that I want to clarify is the usage of the keyword processing unit versus processor. So a core here is an individual processing unit, but all of the cores working together in a multi-core, we call multi-core processor, okay? So I feel like those are words that are easy to mess up because you might think of a core as a processor, but not quite. The book says it's a processing unit, not processor chip, okay? So just want to make sure you guys don't get those confused because I was reading and I was like, let me read that again. So yes. Is the multi-core processor the CPU then? A CPU can be multi-core but doesn't have to be. But most modern ones are. I think it's because we had multi-core, we only had 1 core. So we call it the 1-core processor. Well, no, if we called it multi-core, it was because there was in theory multiple cores. But here's the thing about multi-core stuff. It's pretty new, so a lot of the terminology is still kind of being defined per se. You know, even computers in general are pretty new, and a lot of terminology is still being defined. So that's probably why. But anyways, let's talk about cache. And cache is something that I'm pretty sure there's like an entire chapter on. So chapter 1's kind of like an overview chapter of what you're going to learn kind of thing. And so that's why a lot of the stuff I'm just kind of briefing over, but giving you a little bit about, and then we will explore together. Because again, think about it. We're doing the car mode. I'm just showing you the car, and then we're going to spend a lot of time on the engine, a lot of time on the payload, a lot of time on the control, like steer. And then from there, we're going to go into steering, brake, and acceleration, right? So right now, we're just looking at the car, and I'm just teasing you at the different parts. And cache is like, if I was to think about when I took myself CS 219, the only part that I remember out of the class, like that I actually remembered before refreshing, was pipelining and cache. And I found that those were the most useful parts of the class, I guess, because that's what I remember. I don't know. But cache, understanding cache is an important thing, especially as a programmer. If you were doing low-level programming and things like that, it actually would be very, very important. So what is cache? Yeah, I thought it had to do with whether there was 1 or multiple. It was kind of confusing. Yeah, so it's unfortunate that they use that. But hey, there's 2 chapters entirely on multi-cores and stuff like that. So we will revisit those definitions. But let's focus on cache for a minute here. So I was thinking about how to explain this to you guys without getting too hardcore. But the best thing that I could think about was this example I'm about to do here. But first, let me switch to the iPad. And in my notes, what I wrote as a way to remember it is multi-core is multiple processing units, and each processing unit is a core. So this is what I wrote in my notes as a way to actually remember and understand those definitions. And a lot of this class is just learning definitions. Like I said, it's not a coding class, so yeah. Okay, so and then I even wrote it here because I knew I would forget it. But I was trying to say earlier was a single processor computer, and the photo was the photo that I showed you. Okay, so cache, and yeah, see, that's the last thing I wrote because I was pretty sure that was what we were going to reach. That's why originally I told you guys to just read 1.2, 1.1, 1.2, but then I said read 1.3 just in case we get to it. We might not get to it, but that's okay. By the way, for tomorrow, before I forget, go ahead and read. If you haven't read 1.3, make sure you read it. Then read also 1.4, and then 1.5, because that's one page as well. 1.6, read. We might not get to 1.6, but I'd read it. And I'm personally going to read 1.7 as well, but I don't think we'll get to it. And if we do, that's okay. I'll just start talking about it. And then you can catch up on the reading of that. So read up to 1.6, did I say? Yeah, 1.6. Or 1.7 if you can. Okay? So that's what's going to be the reading. I'll post that, of course, on Canvas. But anyways, so cache. Let's talk about cache. So, okay. What is the speed of light? You guys tell me what the speed of light is. Come on, you guys must know the speed of light, right? How fast light travels. Oh, amazing. No, that's actually the conversion between energy and mass. E equals mc squared, if we shall take as a segue, is, I believe this is energy, this is mass, and this is the speed of light. Wait, is the speed of light here? It's C is speed of light? I think C is speed of light. Or a speed of light constant or something. But not quite what we're trying to do here. So no, what is the speed of light? It must have some speed, right? Because I mean, like they say, like light takes 7 minutes to reach us from the sun, I think. So miles per hour. That's probably not the best one. Yes, I like the one that you guys posted before. 300 million meters per second. Yes. Okay. So 300 million meters per second. Okay? Cool. So let's go ahead and pop the calculator out, which I like using Google for. And let's go ahead and compute this in a smaller unit. Okay, so we got, let's just confirm in case you guys, although I'm pretty sure you guys were right, because I remember like speed of sound is 300 meters per second, and then speed of light is 300 million meters per second. But yes, because this is kilometers per second, so yes, that would be right. Okay, so we got the speed of light is 300. Whoa, I don't know what that means. Okay, so meters per second. Okay, per second. So how long is it going to take for, what is the average speed, if I'm looking at my CPU here, or average distance between the CPU and the RAM? The CPU and the RAM has maybe this much. So let me get a ruler. I'm gonna go on ahead and measure my own CPU here. So I'd say in centimeters, it's about 5 centimeters between my CPU and my RAM stick. Okay? Right, it's Mexico. 5 centimeters. How long does it take for light to travel 5 centimeters? So, math equation. So, how do we figure that out? It's probably not long, but how much? 3 washing machines per second. I think it's more than that. But okay, so let's figure this out. So obviously, let's go ahead and convert here. Before we do it on Google here, we'll do it here. Okay, so we got 5 centimeters. Let's convert that to meters so that it matches the same unit as our measurement here. So 5 centimeters is going to be 0.05 meters, right? Because 50 centimeters would be 0.5. Yeah, okay, yeah. So this is the distance that we want, okay? And this is the distance that speed takes. So what we want to know is, we'll call this C, and we'll call this S, okay? So C times some mysterious X is equal to S. That's essentially what we need to do. So because we want to solve for X, we can just divide both sides by C. So ultimately, to compute X, all we need to do is take S divided by C. And S is 0.05 and divide it by the speed of light. So that's easy. It's not too hard. Okay, so the answer is 1.66666, but you know, we got to move the 0 10 digits down, so we got to put a bunch of zeros in front of it. 1/66. Yeah, you know what? Let's leave it in fraction mode. That's a much better idea. Is that the right fraction mode though? Are we good on that? So let's just, not that I don't trust you guys, but I don't trust you guys. No, I don't know. I don't trust myself either on this. You know, math in the morning is a nifty thing. We move the digit 2 times here. We got 2 zeros there, and then it becomes a 5. And then, yeah, we have to divide both sides by 5. So what is this divided by 5? Then it's 60. Okay, that sounds about right. Okay, cool. Now I trust. Wait, no, you put too many zeros on there. No, you didn't. I just didn't move my commas. Yep, you're right. Good job. I trust you now. Okay, so this is in what? In seconds right now, right? Just to make things a little bit easier on us, because this is a fraction, let's go ahead and convert this to something smaller than seconds. So what can seconds be divided in? So maybe seconds, what would be the Wikipedia article for that? Smaller than second, or second measurements. Well, yes, nanoseconds, but what are the different, I want to pull up a table. What would I look up in Google to figure that table out? Sizes of seconds? No, okay, units. Orders of magnitude, there we go. Okay, so if you look at this, somewhere in here is going to be, that's bigger, seconds. Okay, so seconds is 10 to the 0, okay? So we got milliseconds, that's a good one, because that one is easy to remember, right? We got milliseconds is basically thousandths of a second. So if we remove this 3 zeros, now we're working with milliseconds, right? Okay, let's go further than that into nanoseconds. That's 6 more zeros. So we take 6 more zeros out, and now we're working with nanoseconds. So it takes 1/6 of a nanosecond to achieve this. Now, what's 1 divided by 6? Oh, I put 9. 0.16, which is what we saw earlier. So yes, about. So that's how long it takes for light to travel from my CPU to my RAM. Okay, 1.16 nanoseconds. If we want to go even smaller than nanoseconds, we could. Okay, cool. That's fast, but it's not fast enough. Yes, speed of light is not fast enough. And by the way, electricity is going to go about the same speed per se. There's a little bit of variation because electrons and whatnot, but we'll go with that, okay? How fast do our computers compute per se, okay? So how fast can a computer do a single operation, like a arithmetic computation? It turns out that, well, it depends, yes, but it turns out that we have achieved that kind of speed. And I'll go ahead and research some examples of some of the latest computers that we have on how fast they can do computations. Okay, but one of the ways that you can figure that out is you can think about the clock cycle, which we'll talk about eventually. You know, they see something that says like 2.4 gigahertz. You know, and what that really means is you can potentially do, you know, giga. That would be kilo, mega, gigahertz. So this is an overgeneralization of this, but you could think about it in theory that you could do that many operations in 1 second per se. Okay, this is a little bit overgeneralization. Okay, just assume that. Again, this is in seconds. But in milliseconds or nanoseconds, you could say that you could do 2.4 operations per nanosecond. Okay, you can do 2.4 per nanosecond. Now we're talking about numbers that are, oh shoot, hold on, let me switch over really fast to the Twitch. Sorry, to the Twitch, to the iPad. So here, I don't know. I don't even know what you saw, what you didn't see anymore. Sad face. Oh no, because we switched to the Google, so you did see this, I think. So really, you got your 0.16 nanoseconds, which is the time it takes for the light to travel from my CPU to my RAM, and then suppose that you have a computer that can do 2.4 operations per nanosecond. If it can do 2.4 operations per nanosecond, what does that mean? Well, that we can say that about half of an operation per nanosecond, right? Something like that. Again, these are very close numbers. This is to a point where it actually can slow us down. And so, because this can slow us down, it's not enough to just have really fast memory. You actually have to bring it close to the CPU. And therein lies the uses of cache. Furthermore, to make things worse, RAM is pretty slow. RAM is about 1 millisecond to refresh, I think. And what that means is that if you're trying to do something to it, it takes milliseconds for it to run. That's super slow when we're dealing with nanosecond operations. So we need both cache for fast, because it would be super expensive to make RAM that was faster, and also because we needed to actually physically be closer to the CPU, because otherwise the distance between the CPU and the RAM is long enough that it's actually slow. We've gotten to that point in technology where the speed of light is too slow for our purposes. So because of that, we introduced the concept of cache. And cache is going to be these tiny little memory blocks that are physically next to the CPU, and there's different layers of them, which I'll talk about next time, which are closer and closer to the CPU, which actually get us extra speed because the distance here is no longer 5 centimeters, but perhaps, 10, I forgot for a second, millimeters? Yeah, millimeters. Or 5 millimeters or something like that. It's actually much, much closer physically to the CPU. And then we don't have so much of a problem because light is so slow. I mean, imagine light being slow, guys. It's slow. So, yes. Fastest clock cycle was 10 to the negative 12. That's fast. That would be 0.001 of a nanosecond or a pico. Yeah. So you can see that we can compute so much fast that light is so slow that literally it would take forever to go to the RAM and seek the next piece of data or operation. And furthermore, that actually is a physical limitation on how fast we can make a computer. Because even within the CPU, even within the transistors, light has to flow into the transistor and out of it. That is also some distance, albeit very small, but it is some distance. So there is a limitation with light. Yeah, light is that annoying that it actually slows us down. So anyways, that's where we'll end the discussion. Next time we'll pick up and talk more about cache in detail. And go ahead and read up to there, just so that we have enough material to talk about. Okay? So hope you guys enjoyed it. I will stay here to write down all the people that talked and whatnot. But no, this isn't actually why quantum computers, because quantum computing would still have, I think, the same problems with light, actually. It's more for the amount of processing power. and qubits and fancy things like that. So cool. Thanks for coming, guys. Have a good day, and I'll see you tomorrow at 11:20. I'll stop the recording.